Hey friends, welcome back to CodeOps Trek. Today, we start the first part of our Docker series, which is Docker Introduction. In this part, we will cover Docker Introduction, its history, why it is required, and how it works. So, let's get started. Before jumping into Docker, let's first see how applications were traditionally deployed before Docker. First was the bare metal era. Back in the day, we had bare metal servers. These were physical machines. In a physical machine, we had hardware components like CPU, used for processing, RAM, used for memory, and storage for data, etc. On top of this hardware, we installed an operating system. Since it's a physical machine, we could have only a single OS running at a time. Now, on top of this OS, we had to install dependencies to run applications. For example, if we wanted to run a Java application, we had to install Java on the server. Similarly, for a Python app, we had to manually install the Python runtime. Databases like MySQL or PostgreSQL also needed manual installation and configuration. So that's how previously applications were deployed. Now, the biggest issue with this kind of setup was dependency conflicts. Suppose we had two Java applications, one needed Java 8, while the other required Java 11. Installing both on the same machine often caused conflicts, making it extremely difficult to set up and maintain. Similarly, databases like MySQL 5.7 and MySQL 8 couldn't run easily on the same server due to version mismatches. This same problem occurred with different programming environments, runtimes, and system libraries. To avoid these conflicts, we had to set up multiple bare metal servers, each configured for specific applications. Now, more servers meant higher costs for hardware, power, cooling, and maintenance. Also, many times, servers were underutilized, wasting CPU, RAM, and storage because each machine was dedicated to just one or two applications. Clearly, this was not scalable and led to huge inefficiencies in deployment. To solve this, the next evolution in deployment came virtual machines. In this case, we have a bare metal server. A physical machine that provides the raw computing power. Inside a bare metal server, we have essential hardware components like CPU, RAM, and storage. But here's the key difference: instead of directly installing an OS on the bare metal, we use a software called a hypervisor. So what is a hypervisor? A hypervisor is a program that allows us to create and manage virtual machines on a bare metal server. It acts as a layer between the hardware and the virtual machines, enabling multiple operating systems to run on a single physical machine. So how does a virtual machine work? Let's assume our bare metal server has 8-core CPU, 32 GB RAM, and 2 TB storage. Now, the hypervisor will create multiple virtual machines by allocating specific resources to each. First, it creates VM1 and allocates 2-core CPU, 4 GB RAM, and 250 GB storage. Similarly, it creates another VM, VM2, allocates 4-core CPU, 8 GB RAM, and 500 GB storage. VM3 allocates 2-core CPU, 8 GB RAM, and 250 GB storage. Each VM has its own dedicated hardware and operates independently. One of the biggest advantages of virtual machines is that each VM can run different operating system, like VM1 can have Ubuntu OS, VM2 can have Windows, and VM3 may have macOS. This way, the hypervisor removes the limitations of bare metal deployment by introducing virtualization. There are multiple benefits of using a hypervisor and virtual machines. It solves the single OS limitation because each VM can run different operating system. It allows different dependencies and applications, and each VM can have its own software stack. It utilizes hardware more efficiently because multiple VMs share the same physical server. And virtualization reduces infrastructure costs because fewer physical servers are needed compared to bare metal deployment. While virtual machines solved many issues, they still had some drawbacks, like resource overhead and slow startup times. This led to the next evolution in deployment inside containers. So, what is Docker? Docker is an open-source platform that allows developers to build, package, and run applications inside lightweight, portable containers. These containers bundle everything needed to run an application, including the code, runtime, system libraries, and dependencies, ensuring it runs consistently across different environments, whether on a developer's laptop, testing server, or in production. Docker was originally created by Salomon Hykes in 2013 while working at a company called .cloud. It started as an internal project but quickly gained massive popularity, revolutionizing the way applications are deployed and managed. Now let's see, how does Docker work? In Docker-based setup, we still start with a bare metal server, a physical machine that provides the raw computing power. Inside a bare metal server, we have essential hardware components like CPU, RAM, and storage. On top of this hardware, we install a Linux-based operating system, like Ubuntu, CentOS, or Debian. Instead of a hypervisor, we install a Docker engine on the OS. The Docker engine is responsible for spinning up Docker containers, managing containerized applications, and help container to communicate with the underlying OS kernel. Now let's deep dive into a Docker container. Docker containers are lightweight, isolated environments that package applications along with their dependencies. Each container has a lightweight Linux-based OS image like Ubuntu, Alpine, CentOS, or Debian. But, instead of having their own kernel, containers share the host OS kernel. Each container gets a unique hostname and IP address. For example, if we have MySQL container with Ubuntu base, then this container have a lightweight Ubuntu OS image. It includes all dependencies and libraries required for MySQL and runs MySQL as an isolated service. Similarly, another MySQL container with Alpine base will have an Alpine OS image. If there is PostgreSQL container with Debian base, it uses Debian OS image. This container contains PostgreSQL and its required dependencies. For Java application containers, one container can run Java 8 on Ubuntu with the Java application, while another can run Java 11 on Alpine with a different Java application. A Node.js container can have an Ubuntu OS image and it contains Node.js runtime and required dependencies. So, all these containers can run simultaneously on a single system while providing an isolated environment for each application. Each container runs on a thread of the OS, meaning the number of containers a system can run depends on the number of available threads. So that's how Docker has revolutionized deployment by eliminating the drawbacks of virtualization, such as the overhead of creating separate virtual machines. These containers are lightweight, easy to spin up, and provide better resource efficiency. However, Docker is not the only containerization solution available. There are several other container alternatives, including Podman, Linux containers, Containerd, Rocket, etc. That wraps up our introduction to Docker. We have seen how Docker revolutionized deployment, making it lightweight, efficient, and easy to manage compared to traditional virtualization. In the next part, we will dive into setting up Docker and explore all essential Docker commands step by step. So stay tuned and don't forget to subscribe to CodeOps Trek.